All right, what's up, students? Here's lesson 2 of 2 on exponential growth and decay. So the previous one, we kind of introduced the concept of something growing exponentially, like cutting sheets of paper, or your value of your BMW decreasing by 25% every year. That's a horrible loss of money. Those were two exponential functions. The first one was growth and the second one was decay. So I want to talk about those two situations in more detail so that you guys can actually figure out the equations for what that should look like, and be able to take a word problem and create the equations and maybe sub in a value and solve for either the y or the x value. Okay, so that's what we want to get to today. So the first part I want to talk about here is an exponential function that's is exponential growth, right? So it says here an exponential growth is an exponential function that results in an increasing quantity. Its graph has an upwards curve, and we can see that right here, right? As an example, it's y is equal to b to the exponent x, and the value of b has to be greater than 1. Okay, that is the base that we're putting the exponent to, and as long as that base is larger than the number 1, the y value will always be increasing. What about here? An exponential decay situation is an exponential function that results in a decreasing quantity, and its graph has a downwards curve, right? It's still y is equal to bx, but the value for b here has to be in between 0 and 1. And notice that it's not 0 is less than or equal to and b is less than or equal. It's just less than and less than. So that means b has to be in between 0 and 1, but can't be 0 and cannot be 1. Okay? So that b value actually goes right here. That's b right there. Okay, right here. That's b. In a growth situation, it's 1 plus r, and if it's a decay, it's 1 minus whatever that rate is by decimal, as a decimal. Okay, and this is the equation we're going to use entirely. So what is it actually? Let's talk about it. Okay. So in an exponential growth or decay function, you have, first off, a base t, which is the amount, the total amount, okay? The total amount. Here's going to be the total. Typically, that's what you're solving for, right? Total amounts of sheets of paper, or total amount of dollar value of the car, okay? This here is the initial amount, which you start with, okay? And here is the amount of growth or decay rate, which you have to add or subtract. Make sure you turn into a decimal, okay? Must be a decimal. Let's talk about that. Must be a decimal. And then here is t. T is the amount of time that passes by, okay? If it was in the car situation, that's the amount of years that's passing. Or if we're talking about cuts of paper, then that's the amount of times you cutted the paper, right? Okay. So let's look at some examples. Example 1. It says the population growth of a town is estimated by at 1.84% per year, and the population of this town in 2001 was 11.5 million. What was its estimated population in 2011? Okay, so just by looking at it, I could tell you it's a growth situation. This is an exponential function, right? Because this is the lesson type, but it says growth, so we know it's a growth rate, right? And that's 1.84%. And the population of the town when it started was 11.5 million. Okay, and this is a 2001, and then at 2011 we are asking for what is the estimated population. So let's come in and let's talk about it. So we know that the amount in total is equal to the initial amount and then times 1 plus or minus r to the exponent t. That's the general equation we're going to use, but this is a growth situation, so we are going to do it without the minus, okay? So let's take that out. Okay, so we're now going to add the rate. So let's see if we have everything, right? We're trying to find the estimated population, so that is this, the amount in total. And again, just like any other sub and solve algebraic equation, you have to have everything else. You have to have A initial, you have to have R, you have to have T. Basically, the other side of the equation needs to be all numbers so that you can actually sub in those numbers and figure out what you need to find, in this case, AT. Okay, so let's go down the list, see if we have everything. What's the initial amount of people? 11.5 in millions. What about R? R here is given as 1.84%. But remember, I told you we got to convert this to a decimal. So you want to convert a percent to a decimal, you got to divide by 100. At which point this now becomes 0.0184. Let's fix that 0. It looks like a 6 there. 0.0184. That's the number we got to use here. Next, what about T? Is the amount of time, right? So you could see we're actually looking at 2011, but we started off with 2001. So the amount of time that passes is 2011 subtract 2001, which actually gives us 10 years. Okay? So let's take these numbers, let's plug it into the equation, see what pops out. All right, so we're going to write AT is equal to A initial, which is 11.5, and 1 plus 0.0184, and then we got to put it to the exponent 10. Now, let's follow our BEDMAS properly when you're doing this, right? We've got 11.5 times, and this is 1 plus 0.0184 to the exponent 10. So according to BEDMAS, you got to do brackets first, then you got to do exponents, and then you're going to do the multiplying. Okay, so let's make sure we take everything down in the correct order. So the amount, let's write properly here, in total is going to be 11.5, and I'm just going to take the steps this time so you can see everything go down. 0.0184, that's what happens in the brackets, to the exponent 10. AT is equal to 11.5, and then whatever 1.0184 to the exponent 10 is. And if you do that on your calculator, you're going to get, hit it to the exponent 10, 1.200007351. I'm just going to call that 1.2 because the rest of the decimals are not significant here. Okay. Now we just got to times this by 11.5. And we'll get 13.8. What did we find? Well, we found that, therefore, there will be 13.8 million people. You know, let's be specific, in 2011. Okay. Highlighter. Love that stuff. Boom, boom. Okay, let's talk about example 2. I'm going to try to fast forward things a little bit. I'll set it up, get you to sub in, and I'll just hit pause and show you what the answer will be. Here we go, example 2. The number of yeast cells in a culture can be modeled by N, that's a number, D, right? D is a describer there, is equal to 5,000 times 1 plus 0.25 to the exponent D, where ND is the number of yeast cells present after D amount of days. How many yeast cells will be present after 1 week? Okay, all right. So just by looking at it, I think some of you guys are able to spot that we have an adding situation, which means this is growth. Okay, this is a growth situation. So we are expecting a number that's going to be larger. Okay, after a certain amount of days, we are expecting a larger number. This is a growth situation. It's going to grow from what it starts at, which is 5,000, right? Because that's the initial value. Okay, the growth rate is 0.25, and the amount of days is the letter D there. So let's figure out, what do they mean by D here? The D is equal to 7 days. Okay. Bacteria growth does not stop on the weekends. So it's 7 full days, and let's plug it in. So start with the equation. ND is equal to the initial value of 5,000 times 1 plus 0.25, creating a growth situation, to the exponent 7. Okay, and I'm just going to let you try to do it. And hit pause, try it. And there we go. ND is equal to 23,841.86. What? Well, this is an amount of yeast cells. So approximately speaking, this is a model, right? This represents the growth of it. We are looking at, therefore, after 1 week, there will be about 23,841, maybe I'll change that to 842 yeast cells, right? Because that's an 8 after the 1, so that 8 will definitely push that 1 to a 2. All right. Okay, that's another growth situation. Okay, so let's talk about half-life and doubling, right? Double life. So we got a couple more situations here. So the only thing I want to talk about here that's a new detail is when you have something that's specifically decaying. The most common example in real life is what we call half-life. And in half-life, we are talking about, okay, I get it. It's an exponential decay situation, right? Just like everything else is. Let's say if we're talking about exponential functions. But in a half-life exponential decaying situation, I tell you that the decay rate, okay, is 0.5. Okay, because we're talking about how long is it going to take for you to end up with about half of it remaining. Okay, so what is the half-life? That 0.5 is going to be a given for your B value. Okay, and you'll also have an initial value. The thing is now you have a new wrinkle here, and that is highlighted right here in the green here. Okay, there are two things here. One is the amount of time that we are given. Okay, but 2, that bottom H, this is the amount of time it actually takes for whatever we're talking about to lose half. Okay, that's the amount of time it takes to lose half. This will be typically given to you. This H will be typically given. Okay, and we're going to see that here. So magnesium 27 has a half-life of 10 minutes. There you go. Okay, that's the H. If a sample of this element weighed 20 milligrams at 9 a.m., determine the amount that remains at 9:50 a.m. Okay, so we are talking about time going by and how much will be remaining. Okay, so let's figure out what we need. First off, we need to find AT, so that's good. And A0, what you start with is a 20 milligram amount. It's a sample. It weighed 20 milligrams at 9 o'clock a.m. and determine the amount that remains at 9:50. So the amount of time that passes by is 9:50 subtract 9, which actually gives us 50 minutes. We also know the half-life, okay, the amount for it to lose half of it, which is 10 minutes. Okay, and that's very important. So now if we sub in to the formula, you're going to end up with something that looks like this. 20, and this will be 0.5, because it's a half-life situation. You always just write 0.5. And T is 50. And H is 10. Okay? Just like all the other questions, if you're trying to solve for one of the variables, you have to have everything else. So in this case, you can see after my substitution phase, I actually do have everything else I need. Let's try to take some steps to simplify. 50 divided by 10, I can just change that to 5. So what I'm going to do here is 0.5 to the exponent 5 first, right? Exponent's got to happen before multiplying. That's a very common mistake. Some people are going to multiply 20 times 0.5 first and then put that to the exponent 5. That is wrong. So I want to show you the step. 0.5 to the exponent 5 is 0.03125. And you're going to end up with 0.625. Okay, and you're going to say, therefore, after 50 minutes, 0.625, what's the weight? Milligrams will remain. Okay, here's an exponential decay situation where you are losing an amount, and that's why 0.625 is less than what we started with, which was the 20 milligrams at the beginning. Okay, all right, let's talk about double time, and we are out the door. It says when a substance doubles its amount for every individual time, every interval of time. Okay, this is just like half-life, but we're talking about exponential growth. And the most common thing that people understand about half-life is how long does it take for something to double, okay, in amount. How long does it take for something to double in amount? So we have the initial amount, right? We have the total amount, but B value here is stationary at 2. Okay, that's the amount, the fact that it's going to double. And there are two things in play. This is the amount of time we're going to take, right? The amount of time we're going to take, and D is the amount of time it takes to double. Okay, and this letter D will be given. More often than not, it will be given. Okay, so let's see it. Example 4. Initially, a bacteria culture contains a population of 1,250. Doubling time for the bacteria population is 15 minutes. So determine the population after 1.5 hours. So we are talking about doubling. So let's start off, if you want to write out the formula. And we are going to double this, T over D. Okay, and let's see what ingredients we got. We are trying to figure out the amount that's going to be remaining, so we are trying to find AT, so that's great. That is unknown, but what about everything else, right? A initial, which you start with, is 1,250 bacteria. And the doubling time, D, is 15 minutes. Determine the population after 1.5 hours. T is equal to 1.5 hours. So notice we have a slight irregularity. When you have different time values, that is not acceptable. Okay, you got to be talking about either the same units or fixing them. In this case, we got to fix them. Okay, typically you want to go to the lower, smaller unit just so that your numbers will balance out and make better sense. And if you have 15 minutes and 1.5 hours, let's change the hours to minutes, right? So what you do is you have to times this by 60 minutes per hour. And then the hours will cross out. And you're going to be left with 1.5 times 60, which is 90 minutes, right? If you're waiting around 1.5 hours, that's 1 full hour, which is 60 minutes, and then half an hour, which is 30 more minutes, gives you 90 minutes. That makes sense, right? So T is equal to 90. So let's plug everything in now that we're using time at the same unit, and let's see what we got. Oops. The initial population is 1,250. We are talking about doubling time. T is 90, and doubling time is 15. All right. Let's sub and solve without making mistakes. We're not going to do the multiplying first. We are going to do the exponent. 90 divided by 15 is 6. To the exponent 6 times 1,250. 80, is it? About, come on everybody, did you get 80,000? Okay, so there will be at, well, maybe 1.5 hours, there will be 80,000 bacteria. There we go. This is how you do exponential growth and decay questions. Whenever the word doubling or half-life pops up, make sure you use the appropriate formulas as I've just given here. If not, you're going to revert back to just a straight exponential growth and decay formula, which is this one too, okay? So if you don't see exponential growth or decay described as doubling or half-life, you're just going to use this version. Okay, figure out if it's growth, you're going to use a plus, decay, you're going to use a minus. But if you see the word double or half-life, then you're going to use one of the other two formulas. Right here, half-life is going to be this one, and doubling, you're going to use this one. Okay, I've got a worksheet attached and also some more workbook problems. Again, the workbooks have been taken pictures of as PDFs, and you're going to see that on the following links on our content. So give those all a shot and try them out, okay? Hope this message finds you guys well, and you guys are all doing great. I miss you guys and girls. Take good care, and see you around.